be talking about code signing. So this is the stage name that I'm going to assume for these 30 minutes. So this takes after a publisher name for a Microsoft code signing certificate. So real quick, I want to ask you a question. We've all seen this program before, right? Microsoft Paint. So we kind of implicitly just assume that it's trusted, right? It's benign. There's likely nothing malicious about this. There's probably no way in which an attacker could abuse this, right? So we just have implicit trust that this program's fine, right? It's signed by Microsoft, comes from a trusted publisher. Now, would you ask that same question of every single built-in operating system binary present? No, of course not, okay? So today I'm going to be challenging some assumptions about code signing. So my name is Matt Graeber. I'm a security researcher at Spectre Ops. All right, so let's start investigating a potential event here. So here we're looking at an event log entry from sysinternal sysmon. And let's see if we can find anything suspicious from this entry, okay? So the image loaded was notepad.exe. All right, notepad.exe by itself, there's probably nothing wrong with that. Now, to someone with a trained eye, you might notice, it's kind of weird, actually, that Notepad, which should be present in System32, is being loaded from the Windows tasks directory. Now, only an admin should be able to write to this directory, correct? That may not necessarily be the case. So, you know, that stands out to me as a little suspicious. Now, I didn't want to make this, you know, too obvious that, you know, this might be an actual legitimate Notepad. So I tweaked just one little thing, the company name from Microsoft Corporation to Manifestation Corporation. But what's especially interesting to me is, despite these weird properties that we're seeing, it's still signed by Microsoft. So perhaps we could lower our suspicion levels a little bit because this certainly this certainly appears to have originated from Microsoft. So it should be trusted, right? So here's the same entry in autoruns. So for whatever reason, this seemingly benign executable is persisted in a run key. And there's a switch that you can provide autoruns to validate signatures as well. So indeed, again, this is a verified Microsoft Windows binary. Now, what I have found pretty frequently, what defenders will do, so defenders love autoruns. You know, it has a lot of persistence coverage. But because there can be so much noise, what's really common is to just hide all the Microsoft and Windows signed entries. It's, you know, it should be a fairly reasonable thing to do because there's just so much noise, there's so much legitimate stuff that's persisted to your system, right? So again, kind of weird that Notepad has an autoruns entry, but you know, let's just move on for now. All right, let's maybe dig in a little bit further. Maybe I shouldn't necessarily trust sysinternals. Let's go into the Explorer UI and start digging into the signature. Okay, so again, this appears to be signed. It looks like by Microsoft. Okay, and so indeed, it is a valid digital signature originating from Microsoft. And down here below, it's also time-stamped, which is a very common property of signed code. So everything's looking okay, other than the fact that it's kind of weird that like notepad.exe has been persisted to a run key. Now, you know, for whatever reason, maybe we don't fully trust the output from Windows Explorer. Let's try another signature verification utility, in this case, sysinternal sigcheck. So indeed, as would be expected, sigcheck returns this binary as being signed and originating from Microsoft. Now, no Microsoft binary could ever be used for evil, right? And is this notepad.exe actually benign? Or is there any reason we have to believe that this could be suspicious? But it's signed by Microsoft, so can it really be a malicious binary? I don't know. But indeed, there are many, many abusable signed Microsoft applications. So this shouldn't come as a surprise to anyone. You know, so we have PowerShell. I'm a huge PowerShell fanboy. there's install util, regsvr32, you know, simple ththings like WinDBG, I mean, turns out they're great shellcode runners, right? So the problem is that all of these abusable applications, they have to be manually enumerated, right? So someone like me will go off and abuse PowerShell, various other signed utilities. People like Casey Smith will go find like regsvr32, install util, abuse that, right? And what this enables attackers to do is generally evade detections, right? So all the attackers in the world now are abusing PowerShell, right? So that's like a known thing. But researchers are going to continue to find these new abusable binaries and hopefully evade detections moving forward. Now, again, is it realistic to assume that everything is malicious until proven benign? No. You can't realistically do that with all of the built-in signed Microsoft binaries on the operating system. So why ultimately is code signing important? Well, for better or for worse, defenders generally associate code signing with trust. But that shouldn't be the case. That's not what code signing was for. Code signing is simply an attestation of the origin and the integrity of a signed binary. Nothing more, nothing less. But unfortunately, you know, for better or for worse, security products and defenders treat it as basically like a sole classifier of something being benign, or if not benign, then something suspicious worthy of additional investigation. So this first attack I'm going to describe is basically a way to subvert the way the operating system performs digital signature validation. So there's another component of trust that is just implicit amongst users of computers, right? That the operating system itself should perform digital signature validation properly. Otherwise, then everything falls apart and we can't trust anything. Okay? So a little bit of background about subject interface packages. So now this is only going to refer to user mode code signing validation. And subject interface packages is like an extensible architecture where, say you've got some new file type. So, you know, PowerShell didn't always, it wasn't always a thing, right? But when it came about, Microsoft wanted to support signing PowerShell scripts. So here's this extensible architecture that allows you to sign arbitrary file types where it makes sense for them to be signed. So some of those examples are portable executables, right? So exes, DLLs, device drivers, so on and so forth. Windows script host scripts, so VBScript and JScript. PowerShell, so there's all kinds of PowerShell code that can be signed. And then for everything else, there's catalog files. So a catalog file is basically just a list of hashes that can be signed. So technically, like, you could sign a text file that could have originated from Microsoft. Okay? All right. So again, a little bit of background about subject interface packages, or I'm going to call them SIPs for short. All user mode signing validation generally is going to be performed by calling the WinVerifyTrust function in wintrust.dll. Now, under the hood, all of this is abstracted to developers, this whole SIP architecture. Right? So when you need to sign a PowerShell script, these SIPs under the hood would be like, hey, I'm the DLL that signs PowerShell stuff, so go ahead and give me your signing key, and I'll take care of the rest. I'll store the signature in a blob, and then you can later pull that digital signature out and validate it accordingly, depending upon the file type. Now, there's also kernel mode signing validation. We're not going to get into that in too much detail, but basically, to my knowledge, this is all performed in ci.dll, so a kernel driver that only performs validation of PEs and catalog files. So it's not an extensible system in the kernel, but again, we're just going to be talking about user mode validation. Okay, so the way these are stored is in the registry. And there's two main SIP capabilities that you should really consider, or at least an attacker would want to consider. And the first is cryptsip DLL get signed data message. So when you say validate the signature on this blob or this portable executable, this is the function that retrieves that signature from that specific file, whether it's P or PowerShell script or whatever. And then there's cryptzip DLL verify indirect data, which validates the signed hash in the digital signature. So it takes the hash of the file, compares it against the signed hash in the digital signature, and if they both match, then you're good to go. Additionally, you need to make sure that the signed code chains to a trusted root. And we'll talk about that a little bit later. So all this is stored in the registry in the highlighted key here. And when you dig through these subkeys, for example, cryptzip DLL verify indirect data, you'll find a bunch of GUIDs. And each GUID refers to a specific SIP. So this one here, the one that starts with C689, is the one that is specific to validation of portable executable files. And you can see here that in the registry, there's a DLL and then the implementing function name of the code that performs the digital signature validation. So you might start to get some ideas about how this could be hijacked. I wrote some code that allowed you to just specify the GUID. So here we're interested in all the signing capabilities in user mode for portable executables. And you can see that everything is implemented in wintrust.dll through these exported functions that you can see on the right. Now, some of you may be familiar with the Bad Rabbit ransomware that came out. So one of the things that they did was distribute Mimikatz, and they applied a legitimate Microsoft digital signature to their own code, presumably maybe to bypass some weaker security products that would just be like, oh, this thing is signed, I'm not going to bother to validate the signature, but it's probably still good. So that's what they did in this case. And here you can see that cryptzip verify indirect data function working as it should. It tells you that the digital signature is not valid because the attacker just yanked the signature and applied it to their own, in this case, Mimikatz binary. So here's the implementation of cryptzip verify indirect data. It's pretty simple, actually. So it takes, it receives two parameters. What's passed in those parameters is largely irrelevant, at least for this talk for now. But what you should note is the return value. So at the time, I didn't really know what the purpose of this was. Like, it's not really clear in documentation. So either this function can return true or false. So my assumption was that if it returned true, then the hash validation checked out, and it's a valid signature. So I just went and implemented my own. Super simple. So I don't care what's being passed into me. I'm just going to give it the thumbs up, and hopefully I might be able to pass some checks as an attacker. Now, I'm no fan, generally speaking, of dropping binaries to disk as an attacker if I can avoid it. So I was considering this from like an application whitelisting bypass perspective, where there could be like a chicken and the egg problem, where like if I'm dropping unsigned like hijack code to hijack the signature validation stuff, that it might not load in the first place. I wasn't really sure, but I thought maybe I could do better. The function signature to this cryptzip DLL, cryptzip verify indirect data function is pretty simple, right? So two parameters, and it returns either true or false. And all of this is stored in the registry, right? So like it just points to the exported function name that implements this relatively simple function signature. So the idea I had was maybe spend a few minutes looking at signed export functions where the function takes two parameters, has minimal or no side effects on the arguments passed into the function, and returns true, or the equivalent of true. And in like 5 minutes of searching, I came upon the dbg UI continue export function in NTDLL. So to this day, I don't really know the purpose of this. I could probably go ask Alex Ionescu, he would know. I don't really care because it worked. So here's the difference, right? I just hijacked cryptzip DLL verify indirect data to point to dbg UI continue, which basically just returns the equivalent of true and doesn't do anything to the arguments that are passed in. So here's the before. So we have our notepad totesnotevil.exe working as it should, where in this case I applied, sort of like Bad Rabbit, I took a legitimate digital signature, applied it to my malicious code, as expected, hash mismatch. And then after the hijack occurred, turns out we have a valid Microsoft binary. Now, this is actually really relatively easy to detect. As you saw, we're just hijacking registry values, so if you can monitor those, that's great. These really should never change. There may be cases where in the future new SIPs are added, but the existing ones, like reportable executables and PowerShell code and whatnot, those implementations should never change, or the export function name should never change. And so fortunately, just got a sneak preview from the Defender ATP team. They've got a working detection for this specific attack, which is really cool. All right. So let's talk about our second attack, which is certificate cloning and root CA installation. So the first attack that I covered, you had to be admin. Now, some people might argue with me, well, okay, like the integrity of the system's already been compromised, so it doesn't really matter. Well, it kind of does, because you're going to be fooling a lot of defenders as an admin. And so if you remember like the sysmon and autoruns output, an attacker doing that is really going to effectively blend in, because one of the motivations of me getting into this work was I worked with enough customers where they were needing to triage and baseline security events, and one of the most common ways to filter out all the benign noise was by signer, right? I mean, it's a relatively realistic thing to do, exclude all of the known abusable Microsoft binaries, and then everything else just filter out, right? So I kind of wanted to exploit and take advantage of that, that sort of naive mindset and work on these attacks to sort of shed light on the fact that we should not be implying trust on something that is simply signed. So the next attack actually doesn't require that you be admin, which is kind of nice. But a little bit of background. So in the operating system, there is default implicit trust of certificates, right? So here I have the certificate view up on the trusted root certification authorities. So these are all the code signing certificate issuers that are just implicitly trusted out of the box. Now, Microsoft has a very rigorous process that as an issuer, you have to go through in order to get onto this list. And so that's definitely a good thing. Now, whether or not your organization or you specifically trust something like no liability accepted from VeriSign, which expired a long time ago, perhaps that's something you should consider. But anyway, at the time, Microsoft considered all these to be trusted. And for good reason, like the Microsoft Root Authority certificates. These are the issuers of all Microsoft code signing certificates and SSL certificates. Right? So we need to trust things, otherwise just working the operating system will just be very wonky, right? Like you'll get warnings like when you're browsing to like all the sites on the internet. You'll see that when you validate code signing or digital signatures on code, that nothing will validate. So there needs to be a set of trusted root certificates, and this is indeed the case. Now, as an attacker, why can't I just trust my own root CA? Well, turns out this is really easy to do, and you don't even have to be admin to achieve this attack. So what I did was there's a really convenient PowerShell commandlet, new self-signed certificate, and there's a parameter that's -clone cert. So I just took an existing certificate chain from Microsoft, cloned each one of them. So there's typically 3 in the chain. There's a leaf certificate, the certificate that signs the code. There's an intermediate issuing certificate, and then the root certificate at the top. I cloned all 3 of those, signed each one of those in the chain. So I now control my own Microsoft-ish certificate chain. And then I can simply call something like import certificate, And as a standard user, I can trust my own malicious root CA. Now, you will get, as an unprivileged user, you'll get this pop-up every time. But Casey Smith, sub T, on Twitter yesterday or this morning showed that, well, you can just like hook the message box function to just automate the process of clicking yes on that. So I mean, it's just a simple bypass to that. Now, if you were elevated and doing this attack, you would not see this dialogue. All right, so now I can sign my own malicious code as if I were Microsoft, because all I basically did was just copy all the properties out of the existing certificates. Really the only thing that's different is the public-private key pair, right? I have my own. So to the naive defender who doesn't know to look for this sort of attack, right? Like, what's the difference? But clearly, one of these is not like the other. Now, as an attacker, I maybe could have had a little better OPSEC and matched the validity periods, where the expiration date, I could have just rolled back my clock to match that. So, like, as a defender, like, how would you realistically be able to distinguish between root CA that is trusted versus one that has no business being trusted? And so I'll get back into that shortly. So what do these attacks ultimately buy an attacker? So first of all, as I alluded to previously, these are likely to be overlooked by incident responders and threat hunters. Right, so that case where I had notepad.exe, right, there were some things that looked a little suspicious, but that needle in the haystack would not have stood out at scale, right? When you have over 100,000 of these security events happening, daily, like, you're not going to catch that needle in a haystack. This is likely to subvert many security products, as you saw was the case in the sysinternals tools. Basically, all sysinternals does when one of its utilities does signature validation is pull out the publisher name, Microsoft Windows in this case, and it checks to see if it's valid. So in the first attack, I hijacked the validation function with sort of like a code reuse gadget, like that dbg UI continue function. And in the case of the second attack, well, I just created my own valid certificate chain that has Microsoft Windows in like all the properties. And then I trusted that certificate. So I pass all those checks, like I look like signed Microsoft code. And in some cases, you can subvert application whitelisting enforcement. So there was a case where with the SIP hijack attack, this bypassed device guard in some specific ways, like with PowerShell, for example, or Windows script host. But again, you would have to be an attacker for that, or sorry, an admin to carry out that attack. And unless they are specifically known to be abused, all Microsoft binaries are just implicitly trusted anyway, because it's not realistic to be suspicious of all Microsoft binaries on the system. And lastly, in the case of the SIP hijack attack, this does pose like a persistence mechanism. So if you implement your own validation function, then you can, in my example, I just returned true, but maybe you could have your own malicious code that is executed in the context of any utility that performs digital signature validation. So I'm going to briefly go into how you might investigate some signature anomalies and some data points that are worth paying attention to when investigating these sorts of things. So the first is a hash mismatch. Right, so this is where the signed hash in the digital signature does not match the calculated hash of the binary. And this is, again, the purpose of that crypt-sip-dll verify indirect data function. It does the calculation, performs the comparison, and if they match, then you have a valid signature. Again, assuming it chains to a trusted root certificate. So I'm of the opinion that anytime a digital signature fails to validate, that should be treated with extreme suspicion. Right? So it was the case with Bad Rabbit where they applied a legitimate certificate to the Mimikatz binary. Right? Obviously, there's no reason that should be allowed to execute because the integrity of that binary has been invalidated, right? And that's one of the core, fundamental purposes of code signing. Now, of course, an elevated attacker can just hijack that functionality, but fortunately, I'm just hijacking registry keys, which can be monitored, as is the case with what they're doing in Defender ATP for that detection. Now, an interesting data point is the PE authenticode hash. This is also referred to as authentihash for those of you who have virus total intelligence access. So this is the hash of a portable executable minus the signature blob and 2 or 3 fields within the portable executable. So this is the hash of the code itself before it was actually signed. And so, what makes this an interesting data point is that so you could apply a signature to the same, you could apply different signatures to the same binary, but the PE authenticode hash would remain the same. So an older attack, and this is still used somewhat often, is a lot of malware will just append a configuration to the end of the binary. And what the authenticode hash would allow you to do, if you have access to something like VTI, is you could say, show me all the unique authenticode hashes that have more than one file hash. So that could imply that there's something suspicious going on where data was stuffed to the end of it, or a different code signing certificate was applied to the same binary. And then there's the certificate hash or thumbprint value. So this is just the hash calculation of the certificate itself. This is not related to the digital signature. So the distinction is the digital signature has a signed hash for a specific piece of code in it. This is just the certificate contents. And this is really what should form the basis of certificate trust. So Microsoft publishes all of the default root CA certificates in the form of this file authroot.stl, which can be downloaded through TechNet or something like that. And this is a signed file consisting of all of the certificate hashes of the trusted, or what Microsoft deems to be trustworthy, root certificates. And so what defenders and what security products should be validating is the hash of the certificate, not publisher name and the fact that the digital signature is valid. And this also forms the basis for application whitelisting enforcement. So, for example, you can build a device guard policy where you select the signers that you want to trust, and the way device guard enforces it is by the certificate hash, not off the publisher name and the fact that whether or not it's a valid signature. And then finally, there's the digital signature hash. So I just kind of made this up. It was an interesting data point to me where, in the case of a PE, an authenticode signature is stored as a blob at the end of the file, and there's a file pointer in the PE file format that points to where on disk the signature resides. So if you just hash that signature blob, then this could be an interesting data point where, so this was the case in Bad Rabbit, where I was able to trace the actual file that the legitimate digital signature was stolen from before it was applied to the Mimikatz binary. So I was able, through calculating this hash, I determined that it was an older sysinternals utility where they just stole that blob and then applied it to their Mimikatz, and then they just updated an offset to be like, okay, here's my new authenticode signature. So just kind of an interesting data point to be mindful of. And then lastly, there are timestamp anomalies. So pretty much all signed code is going to have a timestamp. So a timestamp is just like a third-party attestation saying that this signature was valid at the time of signing, like within its validity period. There's only one exception where a timestamp would not be applied, and that is in flight sign code. So like Windows Insider Preview code will not be timestamped, but all production code should have a timestamp. So if it doesn't, then that could be suspicious. Lastly, another anomaly would be where if all the validity periods within the chain all line up to one another. So this would imply that I built the chain one by one, and so this realistically should not happen for a forged chain. So quick call to action. So I think that defenders and security products should take greater care in validating signatures. Again, I said it should really be based on the certificate hash. Again, because these are completely controllable by the attacker, the publisher name, and whether or not the signature is valid. Baseline your trusted root CAs, again, by hash and using that authroot.stl file to compare against. And some quick references. So I go into much greater detail of these attacks in this blog post and white post that I have. So feel free to check that out. And there's some additional detection guidance for these attacks as well. So thank you.